All right, welcome to This Explainer. Today, we're diving into the story of how machines first learned to remember. But it's also a story about a single critical flaw in that memory, a bottleneck that, once someone figured out how to solve it, completely changed the game for AI.
So let's start with a really fundamental problem, something that seems super simple for us humans. If I say a sentence like, "The cat, which had been sleeping soundly all day in the sun, finally woke up," you have no trouble knowing that the cat is what the sentence is all about. But how on earth does a machine do that? It has to somehow remember the beginning of the sentence all the way to the end. It needs a memory, right?
Okay, so the earliest neural networks, what we call feed-forward networks, they basically had no memory at all. Information just flowed straight through, in one direction. Each little piece of data was processed all by itself, completely isolated. And that's a huge problem, right? Because it means they couldn't understand context or order, which is the absolute key to understanding language. But a brand new idea, one inspired by the feedback loops in our own brains, was about to change the whole shebang.
Now, this idea of creating loops for memory, it wasn't actually brand new. You had researchers way back in the 1950s, folks like the visionary Frank Rosenblatt, who already knew that if you really want to imitate the human brain, these networks needed to be able to loop back on themselves. They had to be, recurrent. They knew memory was the secret sauce.
And so, this is where the recurrent neural network, or what we all call the RNN, comes into the picture. Now, the technical definition on screen looks a little intimidating, but it all boils down to one simple, powerful idea. This was a machine designed specifically to handle sequences. Stuff that happens in a specific order, just like words in a sentence.
All right, so what's the big idea here? What's the clever trick that actually gives an RNN its memory? How does it really work under the hood?
Well, it really all comes down to a simple loop. Here's how it goes. The network takes in a piece of the sequence, say the first word of a sentence. It processes that word along with whatever it has in its memory from the previous step. Then, it spits out two things, an output and, this is the crucial part, an updated memory. This memory, which we call the hidden state, gets looped right back around to be used when the network processes the very next word. See? It's a cycle.
And that's really the whole trick. The loop is the memory. That's the big takeaway here. This constant cycle, passing information from one step to the very next, is what lets the network build up this continuous, persistent understanding of what's going on. It's exactly how it remembers the cat from way back at the beginning of our sentence.
Okay, so we've got this machine with memory. So what's the ultimate test you could put it through? Well, how about translation? Taking a sentence in one language and turning it into another. That is one of the toughest sequence problems you can possibly imagine.
So to tackle this massive challenge, researchers came up with a really clever two-part system. It's called an encoder-decoder architecture. The first part, the encoder, is an RNN. Its job is to read the original sentence, let's say an English sentence, one word at a time. And with every single word it reads, it updates its internal memory, that hidden state, trying to soak up and understand the meaning as it goes along. But here's the most important part of the encoder's job. After it's read the entire sentence, its goal is to compress everything it's learned, all the meaning, all the context, all the grammar, into one single vector, a single package of numbers. You can think of it like a super condensed numerical summary of the entire sentence's soul. And that's the final hidden state.
All right, then the second part, the decoder, takes the stage. It gets handed that one single summary vector from the encoder, and that's it. That becomes its starting memory. And from that single chunk of information, its job is to start writing the new sentence, say in French, one word at a time. And of course, it's using its own internal memory loop to remember what it's already written so it doesn't get lost. And let me tell you, this system worked. It was a total breakthrough. For years, these things, especially the more advanced versions called LSTMs, which had a much better long-term memory, they were the absolute workhorses of AI translation. I mean, they dominated the field. It was a huge, huge success. But there was a problem.
A huge elephant in the room. A fatal flaw hiding in plain sight right at the core of this incredibly successful design. I mean, just think about it for a second. Does it really make sense to try and cram all the nuance, all the complexity of a really long, detailed sentence into one single, fixed-size vector of numbers? Really? There's this brilliant analogy that just nails the problem. Imagine someone hands you a single-sentence summary of a giant novel, like War and Peace or something. And then they say,
Okay, now rewrite the entire book using only that one sentence. It's impossible, right? You'd lose all the details, the subplots, the character development, everything. Well, that's basically what we were asking the decoder RNN to do.
And this fundamental problem, this squeeze point where an entire sentence had to be crushed down into one summary, it got a name, the information bottleneck. And it became super clear that no matter how much better we made our RNNs, this bottleneck was holding everything back. It was the ceiling preventing AI from getting to the next level.
So you had all these top researchers in the world trying to find ways to make this system better, to maybe make the bottleneck a little wider, but then an intern, of all people, at the University of Montreal started looking at the problem completely differently.
That intern's name was Dmitry Bogdanov, and in 2014, he basically just called out the whole idea. In his own words, he said, "I was super skeptical about the idea of cramming a sequence of words in a vector." So what did he do? He started thinking, not about how to make the bottleneck better, but how to just get rid of it completely. And that skepticism, that simple question, that was a turning point for the entire field of AI.
So when you look at the timeline, you can see it was a really long road to get here. I mean, from those first ideas way back in the 50s to the creation of the powerful LSTMs in '97 that made RNNs actually work well, progress was steady. But 2014, that was a huge shift. The whole community now had a new mission, a new monster to slay, the information bottleneck.
And that brings us right to the heart of it all. If squishing everything down into one summary is the problem, then what in the world is the solution? What's the alternative? You need a totally new way of thinking. Instead of forcing the machine to remember everything in one go, what if you could give it the ability to look back at the entire original sentence whenever it needs to decide for itself what's important at any given moment? Which leads us to the final breakthrough question. How do you teach a machine to pay attention?